Hi everyone. Uh, Checking my audio levels and we look good. Okay. Um, well, let's start. First, I'm going to start with an apology. I've been meaning to change the intro music and image for a long time. You must be bored of it by now, but I'm going to try to remember to do that by the end of this lecture. But today, what we're going to do is we're just going to look at the energy stuff. That's the stuff, the videos that you should have watched last week, and that one short video earlier this week. And that's it for energy. And for the test, on the I guess yours is on the 29th, a week from today. For the test, it'll be that material and also the material on Newton's laws. Okay, so just Newton's laws, and I guess Newton's laws, the universal gravitational stuff, and the energy. Okay, so I've got two questions today to go over, and the first question is basically one of my usual questions where I've got either a car, or in this case, I've got a cart, and it's just going to go uphill and downhill, and there's some springs. Okay, so there's energy there, and we'll do it first without friction, and then we'll repeat it with friction, and then I've got another one which is a question on energies in an oscillator. Now, we've studied the oscillator before, but now we're going to study the oscillator in terms of energy. Okay, so let's start off here, and let me see if there's any complaints about my audio in the chat here. Please always, like, if you can't hear me or if there's any problems with the audio, just let me know, okay? Is That's the only thing I'm never quite sure of between each live stream. All right, so well, let's read the question and see how to answer it. So I have a cart here, and it weighs 150 kilograms. Okay, and it's placed at rest against a large spring with a spring constant of 17,000 newtons per meter. You know what? I could just as equally have written this as 17 kilonewtons. And I should probably start using some of these because I do want you to get used to kilonewtons and kilojoules and so on, especially kilojoules because that's a measure of food energy used in like Canada and Europe. Here in the U.S. we tend to use for food energy we tend to use calories. So you look at a chocolate bar and it's got like 400 calories. In Europe or in Canada, it'll actually be in kilojoules. So it's important to start thinking in terms of kilojoules. Okay, anyhow, a bit of an aside. So a cart of mass 150 kilograms is placed at rest against a large spring with a spring constant of 17 kilonewton per meter K. Okay, and the spring is compressed a distance of 1.5 meters and then released. Okay, so I think you can picture what's going to happen. The spring is going to push the cart forward, and then the cart travels along some hill, a flat hilltop, a distance of, well, some distance. Okay, and then it's going to go downhill, and it's going to drop a vertical distance of 50 meters to ground level. Okay, and I label some of the points here. And I forgot to turn on my drawing program, but that shouldn't take too long. Okay. So you should be able to do these problems almost without even like drawing a picture, but I think it's a good idea to draw a picture. And so let's switch to my other um, drawing board here like that. And there we go. It showed up. All right. So let me describe again what's going on. Basically, you've got a cart and it's on a hilltop. And so I'll draw this in black. So here's like a hilltop like that, and then it goes downhill like that. Okay. And I tell you that this distance in here is 15 meters. All right, there we go, 15 meters. And I have this spring here like that. I guess it's got to be attached to something, maybe like a wall here like that. Okay. And it's pushing up against the car like that. There's my car like that. All right, terrible drawing of a car, but that's all right. I think you've got the idea. Okay, and so I label a few points there. I label point A, which if you read the question again, point A is, oh, I'll do it in blue here. Point A is like here when the car is compressed. Okay, and then it travels some distance at this, like flat hilltop here like that. And so somewhere along there, this is like point B, and then it goes downhill 50 meters to down here like that. Okay, point C. So we've got these 3 points, and we're going to talk about the energy at those 3 points. Okay, so let me switch back. All right, so let me just make sure that we got it right. The cart has a mass of 150 kilograms. It's placed at rest against that spring, which has a spring constant of 17 kilonewtons per meter. Okay, and that's point A. All right, the spring is compressed a distance of 1.5 meters and then released, and it pushes the cart forward. The cart travels along some distance along a flat hilltop. That was point B that I drew a minute ago, and then it goes downhill, dropping a vertical distance of 15 meters to the ground, and that's point C. Okay, and to start, let's assume there's no friction, and let's take h equals 0 at ground level. And actually, I should probably draw that in there, okay? So when you go to calculate the potential energy due to gravity, the equation for that is mgh, okay? And like the number you're going to get here will depend on where your h is, like where you choose h equals 0. And so like on a test or in an assignment, I'm going to have to tell you where h equals 0 is, otherwise you'll all get different answers, okay? So that's going to be h equals 0 like that. Okay, so h equals 0 is ground level. All right, let's switch back and let's answer the first question. So what's the energy of the system at points A, B, and C? So even before you do any calculation at all, you should realize that without any friction, no energy is being converted to heat. Okay, no energy is being dissipated away. All right, and so the energy at point A and the energy at point B and the energy at point C, and I say energy there, but I could even say the word total energy. All right, although I think it's a little redundant to say that total energy, but the total energy is unchanged. Okay, the kinetic can change, the potential energies, whether gravitational or our spring, they can change, but if you add them all up, that can't change. Okay, and that's the whole point of a conservation law. Once you've calculated the conserved quantity, it's conserved, so that means that it stays the same all throughout the dynamics. Okay, which is what makes life like that's what makes these problems so much it makes problems that are solvable by conservation laws so much easier. Okay, like if you tried to do this with Newton's law, I mean I'd have to give you all the details of that hill and everything. It'd be insane. So okay, so what's the energy? Well, I'm gonna just cut and paste so that you don't have to I don't have to waste a lot of time um, rewriting stuff. Okay, so let's look at this line here first. There we go. Let me highlight that. So the total energy, like I said a minute ago, it's a combination. It's a combination of kinetic, which I've been writing as Ke, okay, and potential, which I've been writing as Pe. Kinetic energy, there's only one kind of kinetic energy. It's the kinetic energy because something is moving. Okay, and so if something is moving, there's kinetic energy. If nothing's moving, there's no kinetic energy. All right, we're actually going to see that again when we even get to rotational kinetic energy. When things are rotating, and we haven't studied that yet, but when things are rotating, they're still moving, and if they're moving, there's a kinetic energy associated with them. The potential energy, that's just because of the way things are configured. Like it's like where they are, or like the fact that the spring is compressed or something like that. Nothing has to be moving for there to be a potential energy. And the potential energies, they can come from lots of sources. So we've only studied two so far. We've studied potential energy due to gravity, which just means like if you're up high, you've got more potential energy than if you're low. Because obviously if you fall, right, like something falls from high to low, well, it could do work. And the higher it is, the further it falls, the more work is done, the more damage it does or whatever, okay? It's got more energy. And the other one is the potential energy due to a spring. So the potential energy can have several sources, okay? And next semester, we'll even study potential energy due to electricity. Okay, so there's still more. Okay, and so then in the next line, what I did was I just broke it up into the two pieces. Okay, so there's the potential energy due to kinetic energy. Okay, sorry, the kinetic energy, 1/2 mv squared, and then there's the potential energy here due to gravity, and there's the potential energy there due to the spring. Okay, now in different problems, like if you don't have a spring in the problem, you wouldn't have to write that in because like there's no spring, it'd be 0. All right, so there it is. Okay, and just plugging in, I said here, the cart is placed at rest against the spring, and the spring is compressed. Okay, so since the cart is not moving at point A, it's up against this compressed spring. We're holding it in place, say. Okay, well then V is 0, so there's no kinetic energy to start with. But there is a potential energy due to both gravity and the spring. Okay, now this sometimes confuses people because you might tend to, like you say, well, it's obvious there's potential energy due to the spring, but why is there potential energy due to due to gravity, and that's just because it's up on the top of a hill. Okay, that's it. All right, so let me switch back here. So I've seen this mistake made in the past. People will say, well, all I have to do is worry about the spring here, because the spring is what's going to push this thing forward and give it kinetic energy. Yeah, I know, but later there will also be a kinetic energy from going downhill. So there'll be a contribution to the kinetic energy that comes from the spring, but there'll also be a contribution to the kinetic energy going downhill. And so you really have to think, oh, well, it's not at ground level. It's not at h equals 0. So if it's not at h equals 0, it's got an MGH. Okay. And so, like I said, it's a mistake that's usually sometimes made, not usually, but sometimes made. And so MGH, yeah, include that. Okay. And what's M? Well, I tell you, M is, what is it here? M is 150. Okay. G, we're always rounding that off to 10 here. And whoops, what did I do here? I accidentally, oh no, redo. Hold on here. How do I do a redo? You know what? Let me just cut and paste it again. I messed things up. Yeah, I messed it up over here actually. Okay, so yeah, I apologize. That doesn't take long to rewrite it. So M is 150, G is 10, and H is 15 meters, like that. Okay, so the potential energy due to gravity is mgh, like that. All right, and then the potential energy due to the spring is 1/2 kx squared. So there's the half. The k, I originally had it at 17,000, but again, I wanted to show you that the k means, kilo there, and so it's 17,000 newtons per meter. That's the MKS version, and the spring is compressed 1.5 meters. That's already an MKS, so 1.5, and so there's the potential energy due to the spring. Okay, and I worked out both of them independently. There's the kinetic energy, so the potential energy due to gravity, and there's the potential energy due to the spring, for a total of 41,625 joules. And like on a test, don't be surprised if you see it, or in the assignment if you haven't done it yet. You don't be surprised to see, like 41.6 kilojoules there. In other words, converted to kilojoules. All right. So if there's any question, let me look in the chat here if there's any questions. Control Z, yeah. I tried that, but for some reason, I didn't get my thing back. But thanks, Riandra. I mean, it usually does work. Control Z usually does work, but it didn't in this case. So, all right. It doesn't look like there's any questions with this. I mean, this is fairly straightforward. Let me continue then with the next one. So the next one is, what's the velocity at point B? Now it gets a little bit more interesting, because you really have to think about, where did that energy go? Okay, so let's switch back to the diagram again. And here you say, well, where did the energy go? At point A, it was pretty obvious that the energy was all potential. It was in the spring, and it was the fact that it was up on top of a hill. Okay. At point B, you say, well, where is the energy now? So you say, well, it's moving, so there's some kinetic energy, so you can't just drop the 1/2 mv squared part, but it's also still in the top of the hill. So there's still energy, potential energy due to gravity. The only thing that there isn't is the potential energy due to the spring, because the spring has sprung, and so that's gone. And so if you go back to the this other whiteboard here, and let me cut and paste, copy here. There we go. Okay, so you still have the same equation, which is basically kinetic energy plus potential, and the kinetic 1/2 mv squared, and the potential, both contributions are mgh and 1/2 kx squared. But the spring has sprung, so x is equal to 0 now, because the spring is no longer compressed. Okay, and I mean, I didn't see that in the diagram, but just imagine, the spring has been uncompressed, and all that energy went into the car, and the cart, and the cart's now moving. So the spring has now x is equal to 0, because it has sprung, but we're still on top of the hill. So h is still 15 meters. All right, and so now plugging in all the numbers, well, I guess I first plugged in x is equal to 0. And if you do that, then this term right here disappears. That's the potential energy due to the spring. It disappears. And all you have is kinetic energy plus potential energy due to gravity. Okay, so the spring is out of the picture. All right, And the rest is just like, plugging in the numbers, but let's go through it. So E, we're at point B now, but E is the same at all the points. Okay, at every single point, it's the same, and so it's still that 41,625 joules. And so E, you could just put that in there. Okay, uh, that's going to equal 1/2 mv squared. We don't know v because that's what I'm asking. What's the velocity at point B? All right, so I have 1/2 mv squared. Okay, so 0.5 times 150 times v squared, which we don't know, plus the mgh, that's still the same as above. Okay, so m is 150, g is 10, and h is 15 meters. And so just simplifying that, that gives you 41,625 is equal to 75 v squared plus 22,500. Okay, and then just like subtract 22,500 from both sides, divide by 75, take the square root, and you get that the velocity is and I put all the digits there, but that's too many. Like, you wouldn't see all of those on a test. I round off to 3 significant figures for the course, but I've got 15.96872, which rounds off to 16 meters per second. Okay, so that kind of makes sense. 16 meters per second. I mean, I don't know what that is in kilometers per hour, but I'm going to quickly calculate that just to give you an idea of what that is. Oh, if I can. 3.6. It's like 60 kilometers per hour, okay, which is pretty fast, okay, but this is a fairly powerful spring, okay, and so, well, there it is, all right, and now the next question is, what's the velocity at point C? So again, like, think about where did that energy go, all right, and the energy now is all kinetic, and you say, well, why? Well, the spring has given up its energy, it's sprung, okay. The potential energy due to gravity, well, that became kinetic because it went downhill. And so now all of the energy is kinetic, all right? So your diagrams don't have to be perfect, but at least so you could see, like, where is all the energy. So, because that's what you're trying to get out of the diagrams. Over here at point A, the energy is all potential, part of it in the spring and part of it in gravity. At point B, the energy is partially kinetic and partially gravitational potential. And at point C, it is all kinetic energy. Okay, and so that's important because, like, you might say, yeah, I know that the energy is all the same, but if you don't know where it went, then you won't be able to answer the question. Okay, so let me cut and paste that answer. All right, so I didn't have to write in the potential energy because we know that it's zero, but I just wanted to show you that, you could start from the same formula. E is equal to 1/2 mv squared for kinetic energy plus mgh plus 1/2 kx squared for the potential energy. But the spring has sprung, so x is 0, and the cart is at ground level, so h is 0. So if you put h is 0 in there and x is 0 in there, the potential energy drops out and it all becomes kinetic. Okay, so now all the energy is kinetic here like that. All right. Now, the energy is still the same. Okay, I mean, the total is still the same. It's still that 41,625 joules, and that's going to equal to 1/2 150 times v squared, like that. And solving for v, it gives you 23.6 meters per second. Okay, so it's moving along pretty fast. Actually, I made my numbers a little kind of big. Let me see what that is in kilometers per hour. Yeah, that's like 85 kilometers per hour. I mean, it's nearing highway speeds is 100, but it's going pretty fast. Okay, so there you go. That answers the question up to that point here. Okay, so up to now there was nothing to do with friction. There was no friction at all. All right. Let me see if there's any questions there in the chat. Nope, people are good. All right, so the analogy that I've used, I might have used it in the pre-recorded lectures, is I think of energy as like you might think of this as like 3 cups, 3 glasses. There's a glass that represents the kinetic energy. There's another one that represents the potential energy due to gravity, and another one that represents the potential energy due to kinetic friction. You've got so much water, and you're just sloshing the water back and forth. The total amount of water remains the same. But whether it's in one glass or another glass or another glass, it depends on the situation. So you look at the diagram to just say to yourself, where did all that energy go? And then you just use the equation for that particular energy. Okay. All right. So let's continue. And I say now, assume there is friction. Okay. And if the card is found to have half the velocity that you found in part C, okay, so we found a velocity of 23.6 meters per second. So if it's found to have half of that velocity, how much energy is lost due to friction? Okay, so we're kind of going to run the problem backwards. At this point, we're at point C, and so if you go back to point C, the energy is all kinetic. It's still all kinetic. The amount of kinetic energy is going to be different. Why? Well, because all the way along here, all the way along this path, I guess I can do it in red, there was a little bit of energy being lost. Now, the word lost, I always say it in quotes because it's only lost if you don't know where it is. It's like, do you lose your keys or do you misplace your keys? Okay? So it's not really being lost. What's happening is all the way along here, because there's friction, there's a little bit of energy that becomes heat. Okay, so there's a little bit of energy becomes heat all the way along that path, and it looks like the energy at the end is less and it's lost, but it's been converted into heat. The thing is we don't know how to do that calculation. Okay, we don't know how to deal with heat yet. That's the subject of next semester, but we could do a little bit. We can at least say, yeah, okay, some energy was lost as heat. Okay, and how does that work? Well, the energy is all kinetic, although there's less of it. So we could still use that the energy, the total energy at the end, is E is equal to 1 half mv squared. There's no mgh because it's at ground level, and there's no 1 half kx squared because the spring is totally out of the picture by this point. Okay, and so let me get that. I hope I'm not going too fast by cutting and pasting. I just don't want to either waste your time or make an error in typing here. But if I'm going too fast, feel free to just slow me down. That's kind of the point of these live chats. Okay, so if the velocity is half of the velocity from the previous problem. Okay, so the velocity when there was no friction was found to be 23.6. Okay, and so I said, well, it's half of that. It just turns out to be half of that. So I kept a lot of the digits there because there's a bit of a round off error if you don't. But basically, that's like 11.8 meters per second. So if you were doing this as an experiment, you could easily do these calculations and say, oh, okay, we anticipate that our cart will be traveling at 23.6 meters per second when it gets to the bottom of the hill. Okay, and you could measure that, using some equipment and measure it. And you get to the bottom of the hill, the cart gets to the bottom of the hill, and you measure its velocity, and it turns out to be 11.8. You go, well, what happened? Well, it's pretty obvious. The energy was lost to heat. Okay, the energy became heat. Okay, because of friction. All right. So the energy now, it's all kinetic. Okay, actually, could just say that here. Oops. It's all kinetic energy at point C. All right. And so E is equal to 1 half mv squared, no mgh, no 1 half kx squared. And just plug in the numbers here, a half, 150. And I kept a lot of those digits there because otherwise I think I would be off by like 40 joules. Not that that's a lot, but I figured what the heck, I'd get it more accurate. And so you find that the energy is 10,406 joules, okay? Which on a test you may see written as like 10.4 kilojoules, like that, okay? So, because the numbers can get pretty big, energy numbers can get pretty big. A joule is not that big, okay? I mean, I don't know what the conversion is between food calories and kilojoules, but they're pretty close. Okay, so there's a lot of energy in food. Okay, so anyhow, all right, so there's the energy, and now you say, well, how much was lost to friction? Well, if you take a look at the delta E, that's going to be you calculate a change as like your final minus your initial. So you had your initial energy which would have been the energy before any of it was lost to friction, and that was that 41,625 joules, okay? And then there's the final energy, and the final energy is at the bottom of the hill after it's lost some of its energy to heat, and that turned out to be only 10,406 joules, so the difference between the two is 31,219 joules. The negative there meaning that the energy decreased, and that's what became heat, okay? So, all right, there we go. And, well, that answers this one. So how much energy was lost to heat, okay? The better wording would have been converted to heat, because heat is a kind of an energy, but that's all right. For this semester, we're good, okay? And then at this point, it's like, well, there was friction. How much friction was there? Well, friction is a force, and there's a relationship between force and energy. And you know, in all the problems I've done, or a lot of the problems I've been doing, you know, we don't have to go back to that work energy theorem. The work energy theorem is kind of theoretical, and you wonder, why did I throw it in there? Like, you know, can't you just show me how to do the problems? Well, yeah, I guess I could, but you kind of want to know that there's a relationship between force and Newton's laws and energy. Okay, energy didn't just fall out of the sky. Energy was actually derived from Newton's laws. Later physicists, you know, discovered that, hey, there's this conserved quantity energy, and it can be derived from forces, and that's where that all came from. And here in this problem, with friction, you have to relate energy and forces again, and that's done through this formula right here. Okay. I mean, it's kind of short, but the answer is kind of short, but it's right here. Okay. So it's basically this WF that I've written there. That's the work due to friction, okay? And so I've got a few terms now. I got like energy, work, and force. And you say, well, what's the relationship? Work is kind of like it's kind of like the transition between one type of energy to another, okay? So because this energy was being transferred from, you know, the kinetic into heat, there was work done. Work is what causes the conversion from one to another, okay? But it still is energy. It's measured in joules. So the work due to friction, WF, I derived that in, that last lecture you saw, is equal to minus F, and I guess I should put a little F there like that. It looks a little funny, but all this means is the force due to friction, okay? So the work due to friction is equal to the force due to friction multiplied by the distance over which it acted, okay? Now, technically with work, there's a cosine theta in there, but that's actually the negative sign. The negative sign is the cosine theta, and the reason for that is because the displacement d is in one direction, and the force is in the exact opposite direction. If you move something one way, the force is always in the opposite direction. And you say, well, what's the angle between the two? It's 180 degrees, okay? And cosine of 180 degrees is negative, so that's where that negative sign comes out, okay? So I mean, basically that I just an explanation for how that formula is derived. But if you just want to use it, you say, well, what do I put in for the work due to friction? Well, that's the energy that became friction, okay? So there's the work due to friction, was just that energy right there, okay? And so there it is. And then the force due to friction, well, that's what we're trying to solve for, like that. And the distance over which it acted, well, that I tell you is 500 meters, okay? And you see the negative signs cancel out, and you get that the force due to friction is 62.438 newtons, which, I mean, I should probably just round that off, 62.4 newtons, okay? Which, it's really an average, you know, but basically along this path, you know, on average, the force due to friction was 62.4 newtons. Now, what is that 500 meters? Okay, so you might say, well, where did that come from? Let's go back to that diagram. You see the red line there? That red line, it doesn't have to be a straight line, but that red line is basically the path over that the car went over. Okay, it's basically the hill. Okay, and all along this path here, all along the path, friction was acting. So the 500 meters is really a measure of like the distance over which the the force of friction acted. Okay, the drop might be only 15 meters, but the entire distance there turns out to be, well, it turns out to be, I don't know, I just said it was 500 meters, which is like half a kilometer. All right, let me see if there's any questions in the chat. No, people look pretty good with this. All right. So if you're good with that, then I can move on to the next question. Okay. Now, what can you expect to see on a test? Variations on this. Okay. I guess I could maybe just mention. We got time here. Maybe I could just mention like a variation, an interesting variation. I don't know if I mentioned this in the pre-recorded lecture, but let me just switch to my diagram here. I won't actually solve a problem like this. I'll just mention it in passing. Whoops, what did I do here? Okay, there we go. Okay, think about this problem. Okay, so we have something at ground level here like that, and we've got a spring like this. Okay, and there's like that, and we got a block here like this. All right, and I think you can see what happens. This has been compressed. Let's say that this is originally compressed to distance x. Again, I'm not going to do it, so I'll give you some symbols here. So the spring has been compressed to distance x like this, and what happens? Well, it's going to get sprung, and it's going to go up into the air here like that. This is my block. Whoops. Try to draw it to scale here like that. So this is sprung up here like that. Okay, so it's gone up a distance h like this. Okay, and you want to know how high does it go before it stops and comes back down. Well, stops, you know, is zero velocity, 0 meters per second. Okay, and so this is a kind of an interesting problem. You go, well, how do I do this? Well, no friction. Okay, just ignore the air friction. Okay, and you say, well, how do I do that? Well, the way you would do this is like you'd say, well, what's the energy down here? Well, the energy, oh, I guess I got to give you a ground level. Let me do that first. Okay, so like this. Oops, I lost my S. Okay, so this is like ground level here, like that. Zero. All right. Okay. And you say, well, what's the energy down here? Well, the energy down here, there's three pieces. There's 1/2 mv squared. There's mgh. And then there's the spring, 1/2 kx squared. Okay? And you say to yourself, okay, let's go through them all. Let's go through each one of them. What's the velocity down here? Well, I'm picturing this thing as kind of being held in place. Okay? And so, you know, the block is just sitting there in place. And so the original velocity is 0. And so it has no kinetic energy to start with. All right? And then you say, all right, well, what's its gravitational potential energy, the mgh? Well, you know what I said? I know the ground is down here, but don't worry about that. You could choose h anywhere you like as long as you're consistent. Okay, so I'm going to say, you know what? Choose h at like the point where you've compressed it. I know that you might say, well, should I choose h up here? Nah, just choose h at the point where it's compressed. And so there's no mgh. And so initially, all the energy is spring potential energy. Okay, and then it goes up, and now in the middle here there's some velocity. The velocity is not zero, so it starts with, here, let me do that in blue. It starts down here with a 0 velocity. Okay, in the middle it has some velocity, but when it gets back to the top it's got no velocity again because it stops at the top of its path. And so you say, okay, well, let me do the whole thing again. So I've got E is equal to 1/2 mv squared. You've got mgh, and you've got plus 1/2, whoops, 1/2 kx squared like that. And you say to yourself, all right, what energies do I have? Well, there's no kinetic because it stops at the top. There's no spring because the spring has given up its energy. And so at the top, the energy is all potential energy. And so this is kind of cool because if you think about this from a dynamics point of view, that is like where the energy is. The energy starts off as all spring. In the middle here, like in the air, the spring is like half sprung, and there's some kinetic energy, and there's even some potential energy because it's off the ground. It's off at h equals 0 or above h equals 0. So up here it could be a combination of all three of them. It's moving a little bit, so it's got some potential, sorry, kinetic energy. It's moving a little bit, so it's got some potential energy. It's got some height to it, so it's got some gravitational potential energy. And the spring might not have completely sprung yet, and so it might even still have some spring potential energy. And it could be a combination of them. And then in the middle here, when it's like there, the spring might be out of the picture, but then it's a combination of kinetic energy and gravitational potential energy. And then when it gets to the top, it's all gravitational potential energy. So it's kind of interesting because the energy is sloshing back and forth. And if you get caught up in the details of what's happening there or what's happening there, you lose sight of the fact that it starts off as all spring and it becomes all gravitational potential energy, making solving this problem actually pretty easy too. Okay, so I didn't use numbers here, and it's probably better that I didn't, so that you don't lose sight of you don't get caught up in the details. But this is the way you should be thinking about it. You should think about it. Well, there's different places the energy can go. Where is it at each point in the cycle or at each point in the dynamics? And then you can calculate it from that. All right. So let me see if there's any questions with that. I mean, I'll just give you an example here, and you can multiply these examples, like you can increase the examples, but the logic is always the same. Okay, so let's do another problem. It'll be kind of a shortish class, I guess. Let's do another problem, and this one is a simple harmonic motion, energy. Okay, so maybe a bit of a description before I jump into it. There's a couple of things that you learned when we use energy on a simple harmonic motion. So originally, I just gave you the kinematics of simple harmonic motion, and it was like, the thing bounces back and forth, and there's a relationship between maximum velocity, maximum acceleration, amplitude, the period of the motion, and angular frequency. Okay. Then in the last lecture, I said, well, now that we know about dynamics, we know about forces, there's actually another relationship I can bring in, and that is if you attach a spring with spring constant K and you pull something out, it'll actually make it oscillate back and forth. Okay. Now for the non-calc students, I can't prove that to you, but for the calc students, I can. Okay. So basically, springs give rise to simple harmonic motion. You might not have known that. You might not have thought that if I take a spring, so a spring's like at equilibrium like that, and I stretch it, and I go, you might not have realized that that gives rise to simple harmonic motion, but it does. Okay. And then the other thing we said was, okay, now I know that there's a relationship between the force of a spring and simple harmonic motion. The other one was, well, what about energy? And the energy as an oscillator goes back and forth is just like the velocity goes from zero at the endpoints to maximum in the middle to zero at the other endpoint, like that. Okay. The kinetic energy goes from zero at the endpoints, maximum in the middle. Okay, so zero, maximum, and zero, like that. And the potential energy does the exact opposite. It has to, because the sum of the two have to add up to a constant. So the potential energy is maximum at the endpoints, it's zero in the middle, and maximum at the other endpoint. And that does the exact opposite. And so the energy basically slashes back and forth from all potential at one endpoint, all kinetic in the middle, and all potential at the other endpoint. Somewhere in between, where it's not at either the endpoint or at equilibrium, it's a little bit of both. It's a little bit kinetic and a little bit potential. Okay, and so that's what this problem is going to try to get at. Okay, so let's do it. So an oscillator, some generic oscillator. Oscillators are everywhere, by the way. Like anytime you knock something and it wobbles back and forth, it's acting like an oscillator. Okay, so everything from the tiny little cilia in your ear, those little fibers which vibrate back and forth, which is how you can hear me right now, to I don't know, skyscrapers bobbing back and forth. Okay, they don't do it very fast, but they do. There's always some kind of elasticity there, so they'll bob back and forth. All of those things are oscillators. So it's kind of hard. I mean, I guess I could pick one particular one out, but generically they're like everywhere. So I just say an oscillator. So an oscillator with a mass of 150 grams, okay, is found to have a period of 0.37 seconds. A period is like if it starts at one endpoint, goes to the other one, and then back again. That full cycle takes 0.37 seconds. Okay, so that's called a period. Okay, when it is 2.5 centimeters from equilibrium. So equilibrium is in the middle. Okay, and it's going to be displaced to one side and to the other side. Okay, and so when it's 2.5 centimeters from equilibrium, it is found to have a velocity of 0.5 meters per second. Okay, and so it then answers the following questions. All right, so the first is, what's the angular frequency? All right, now the reason I asked that right up front is because all of these formulas, you remember even from before, they're all connected together by that omega. So even though omega is not something you measure in the lab, the period is, but the angular frequency comes up over and over and over again in the formula. So even if I don't ask for it, you're going to wind up calculating it. Even if I don't ask for it directly on a test or something, you're still probably going to wind up calculating it. Okay, and so the relationship between your angular frequency and your period is this formula right here. Okay, so we saw that from kinematics, and it's still with us. Okay, so remember when I said at the very beginning, or you may have forgotten that this test is going to emphasize energy and Newton's laws, but some of the stuff from our kinematics naturally comes over. It doesn't go away. Okay, so don't just mind dump all of the stuff that we learned in kinematics. Okay, so the relationship between the angular frequency and the period is given by this formula, omega. That's the symbol for uh, angular frequency. Omega is equal to 2 pi over capital T. Okay, and so it's just a matter of plugging in. Omega is equal to 2 pi is 3.14 divided by 0.37 seconds, and that gives us an omega of 17 hertz. Okay, so there it is. Now hertz, I think you know this, but hertz is the same as per second, like that. Okay, a reciprocal second. All right. So the next question is, what is the spring constant? Okay, and that's one of the new formulas that came up. All right, and it comes from this idea that a spring is what causes simple harmonic motion. All right, and that formula is basically this one right here. It's that one. Whoops, that one right there. Hold on. There we go. Okay, so basically omega, our angular frequency, is equal to the square root of k divided by m. All right, so so I asked for what is the spring constant. That's k. All right, so maybe you should get straight in your head what the symbols are for each of these. So for angular frequency, it's omega. And for spring constant, it's k. Mass is m. That's obvious, all right? So we rearrange that formula. When I draw these kinds of like arrows like that, um, they just mean like if I'm rearranging this. So I just rearrange this. If I square both sides, I get omega squared is k over m. And then I want to isolate k, so I multiply both sides by m, and I got that k is equal to m omega squared. Okay? So that's how you can get k out of both the mass and the angular frequency. Well, we have the mass. I told you that it was 150 grams. And be careful, we need it in kilograms. Okay, so 150 grams is 0.15 kilograms. Omega is, we just found that, it's 17. We need to square that, and that turns out to be 43.35. Okay, the MKS units for spring constant, we saw them already in my previous problem, but they're newtons per meter. Okay, so there it is so far. Let's see if there's any questions in the chat here. Nope. All right. Okay, so great. Now we've answered question B. What is the spring constant? All right. So now what's the total energy of the system? All right. So the energy of the system, cut and paste this. Maybe I should write it this way first. It's kinetic energy plus potential energy. Okay, that's its most general form right there. Okay, all right. So then you say, well, let's more specifically, how do you calculate kinetic energy? Kinetic energy is always calculated the same way. It's always 1/2 mv squared. So there it is. There's the kinetic energy. And now you say, well, what's the potential energy? Well, this is the potential energy of a spring. Even though in the problem, like if you read the problem, like if you didn't know, if you hadn't watched the lecture or anything like that, all I say is oscillator. You go, well, where is there a spring in there? Well, it doesn't matter. Even if they're like in those little cilia in your ear, okay, the little cilia. It's not if you look down there that you're going to see a little spring, like a coiled up spring. The stiffness of the fiber itself is the spring. Okay, and so like whatever's causing the kind of stiffness to the object, like like a skyscraper. Okay, obviously a very rigid object, but not 100% rigid. Okay, so insofar as it can flex, it has a spring constant K. Whatever that flexibility is, whatever is giving the flexibility to the thing, that is the spring constant. Okay, and all oscillators have some flexibility associated with them, because if they were infinitely rigid, they wouldn't oscillate. Okay, and so as soon as you hear oscillator, you should think spring constant. All right, there has to be some flexibility. If there's some flexibility, then there's some spring constant. I mean, I just try to help your intuition here to say, well, why is there even a spring constant with an oscillator? Well, that's why. Okay, and so down here at the potential energy is due to the spring constant. Okay, it's due to the fact that the oscillator is stretched out and then compressed and so on. Okay, and so the potential energy for a spring is 1/2 kx squared, and so ta-da, there it is. It appears even for an oscillator. Okay, so the potential energy is 1/2 kx squared. The kinetic energy is 1/2 mv squared. The potential energy is 1/2 kx squared. Okay, it doesn't matter that this thing is swinging back and forth fast or slow. I know that it's not going to be at a value of x for very long, but it doesn't matter. At that instant, it has that much potential energy. Okay. And so, okay, so now all we have to do is basically plug into this, and we'll get our answer. Okay, so 1/2, that's 0.5. The mass was 150 grams, or 0.15 kilograms. Okay, the velocity, I said, so let's read here what I said in the problem so you know how I plugged it in. I said when it is at a distance of 2.5 centimeters, that's your x, 2.5 centimeters. Then it's got a velocity of 0.5 meters per second, and that's your v. Okay, and so your v here is 0.5 meters per second. All right, and then well, that'll give us the kinetic energy. All right, which turns out to be that number right there. All right, and then for the potential energy, 1/2 kx squared. So the half is 0.5. The k we found above. Okay, so that's 43.35. Okay, and the x, this x has to correspond to this v. And so when the velocity is 0.5 meters per second, because it's changing, right? The velocity is not static, it's changing, speeding up, slowing down. But when the velocity is 0.5 meters per second, then it is 2.5 centimeters from equilibrium. Okay, so we have to be in MKS. So 2.5 centimeters is 0.025 meters. Okay, but that's why I put the x there and v there. Okay, so once again, go back to the language here and read that part that I have highlighted there. When it is 2.5 centimeters from equilibrium, that is when it is 0.025 meters from equilibrium, then it is traveling at 0.5 meters per second. Okay, it's only an instant, but that's good enough that you have now enough information to calculate the energy at that instant in time. And that turns out to be, well, there's the kinetic energy part, there's the potential energy part, and when you got them together, it turns out to be a small energy, but not zero, obviously, 0.0323 joules. Okay, and so here's where conservation of energy comes in. It's not going to be at it's not going to be at that 2.5 centimeters and 0.5 meters per second for very long. In fact, that's just an instant in time, but it doesn't matter, because the energy calculated at that instant is the same as the energy at the next instant and the next instant and the next instant, right? Why? Why is the energy the same at all those instances in time? And the answer is because energy is conserved. Okay, the kinetic energy will change, the potential energy will change, but when you add them together, you'll get a number that doesn't change no matter where you are in the cycle. Okay, so that's the way you should be thinking about this. If you get the total energy anywhere in the cycle, you've got the total energy everywhere in the cycle. Okay, so there we go. There's the total energy, and that answers that question. All right, what is the amplitude? Well, the amplitude you can get from the energy, because all the energy at the endpoint here is all potential. Why? What happens at the endpoints? It stops and turns around. Well, it stops, V is 0. When V is 0, kinetic energy is 0. At that instant, okay, again, it's not going to be there for very long, but still, at that instant, when it's at the endpoint, it's got no kinetic energy. It's all potential. And so you can use this equation here, okay, like that. And you go, wait, where did that A come from? Above I had X. That's right, I had X. But what is X equal to at an endpoint? Well, x at the end point is the amplitude. That's what you mean by the amplitude. Amplitude is the furthest you're going to get from equilibrium. And so when you get to the end point there, x is equal to a. And so the formula for the potential energy is 1/2 kx squared, but x is equal to a at the end point, and so you could just write this. Whoops, that like that. So the energy is equal to 1/2 Ka squared. All right. And where's the kinetic energy part? Well, there isn't any. All right. So now what? Well, I'm just going to rearrange this equation because we're solving for what? What are we solving for? Well, I asked for the amplitude, so we're solving for A. Okay. And we have the energy. So I guess I could have put the numbers in, but I don't know. I like rearranging my formulas with symbols. It's easier than rearranging them with numbers, but whatever works for you. So basically, just take E is equal to 1/2 Ka squared. Multiply both sides by 2 to get rid of the halves. Okay, so then you get this. Let me do it in steps here. I don't know. I always feel like I might be going too fast for you guys, and you're all being too polite to tell me. So, we have this, multiply both sides by 2, and we get 2e is equal to Ka squared. Then divide both sides by k, like that. So 2e divided by k is equal to a squared. Then I take the square root of both sides, and I got that a is equal to the square root of 2e over k. All right, and then I plug in the numbers. Okay, so if you like plugging in the numbers like directly into this equation, it doesn't matter. You'd still get the same answer, but whatever. Okay, and the answer turns out to be when you actually plug it in and work it out in MKS, you're going to get, I'll put the meters in there. You're going to get 0.0386 meters. Okay, which I converted to centimeters, 3.86 centimeters. All right. Now you ask yourself, does that make sense? All right, does it make sense? Well, it has to be bigger than 2.5. And you say, well, why? Well, take a look up here. At 2.5 centimeters, this thing is still moving. So it still can go further than the 2.5 centimeters. Okay, so you know that it's at least going to be at 2.5 centimeters. If this number here, where is it? If this number here had turned out to be less than 2.5 centimeters, then you know you made a mistake, because you know that it's at least going to get to the 2.5 centimeter mark. So you don't know where it's going to go to, but you know that it has to be bigger than 2.5. Okay, so that's at least a check. It's not a perfect check, but it's a little bit of a check. And it turns out to be 3.86 centimeters. So you go, yeah, that sounds sort of right. Makes sense. It's at 2.5 and it's still moving. So here's equilibrium. Here's equilibrium. And, it's at 2.5 and it's still moving. So it's going to go a little bit further. It gets to 3.86. Okay, good. So what's the maximum velocity? All right. So, here's my equilibrium, my finger. This is the oscillator going back and forth here. At the end point here, that's when it's all potential. In the middle, it's all kinetic. It's all kinetic. Why? Because in the middle, x is equal to 0. If x is equal to 0, the potential energy drops out. Okay, it's all kinetic. All right. And so there we use this formula. E is equal to 1/2 mv squared, because it's all kinetic. There it is. Okay, so all kinetic energy. All right, and I actually could have written here V, instead of V, I could have actually written V max. Okay, in fact, let me do that. Let me put that in there just like that, V max. Okay, and then all I did was, I multiplied both sides by 2, divided both sides by m, and that isolates V max squared. And then take the square root of both sides, and I got that V max is equal to the square root of 2 divided by square root of 2e divided by m. Plug in all the numbers and you get 0.7174 meters per second. And I would round that off. It's not that important. You ask yourself, does that make sense? Does that make sense for a maximum velocity? Well, let's take a look here at what the velocity was up here. It was 0.5. Okay, you expect that this number is going to be bigger than 0.5. Why? Well, it's at the 2.5 centimeter port and it's traveling at 0.5. So, if it were going one way, it would go past the 2.5 centimeter mark. It actually gets to the 3.86. On the way back, when it passes the 2.5 centimeter mark, it's going again 0.5 centimeters per second. But by the time it gets to the middle, it's going to be going faster than 0.5. So it turns out that it's going to be going 0.7, 0.7174. Okay, so yeah, that makes sense. It makes sense that, at 2.5 it's only 0.5, so in the middle at equilibrium it's going to be going faster, and so you expect that number to be bigger. If you got smaller, you go, oh, something went wrong. Something went wrong. Okay, so all right, there we go. That's that one. And then one last question, just to show you that once you know the energy at one point, you can use that energy at all points. Okay, so how far from equilibrium is the oscillator when its velocity is 0.6 meters per second? So what am I asking for? How far from equilibrium? How far from equilibrium? I'm asking for, move this up here. How far from equilibrium? I'm asking you to calculate x. X is equal to what? Okay. You say, well, how do I do that? How do I start? Energy. It's always energy for these types of problems. Okay. So start off with your statement that energy is conserved. There it is. That's the statement that energy is conserved. It means basically E is constant throughout. For every V and every X, E is the same. Okay, great. So do we have E? Well, yeah, we do. That's what we calculated up above here. Where did we do that? Here it is. There's our total energy. Okay, so that remains the same. So down here, so 0.0323, down here for the total energy, we put in 0.0323. Great. That's got to equal what? That's got to equal the kinetic energy. There it is. And it's plus the potential energy. There it is. Okay. Now for the kinetic energy, we actually have all the ingredients that we need to work it out. So that 1/2, that's 0.5. The mass, that's 0.15. Gave you that above. And the V, I told you that. I said here, at this point, whatever this x is, this thing is going at 0.6. Okay. Okay. Above I said 0.5, but now I'm saying 0.6. So over here, we put in the value 0.6. All right, for the velocity. So 1/2 mv squared. Okay. And now what about the potential energy? Well, we know, well, there's the half. We know K because we calculated that above, and that was 43.35. We don't know X. That's what we're solving for. Okay. And so the rest is just simplification. And so there's, the energy still on the left-hand side. And then there's a simplified right-hand side. Okay. And then I simplified it a little bit more. All right. I think you guys know how to do this, the arithmetic on your own. Okay. And then, take the square root, and eventually I got 0.01564, which if I convert to centimeters, because I've been working in centimeters, okay, it turns out to be 1.564 centimeters. Does that make sense? Does that make sense? You know what? Let's go to the whiteboard and I'll show you that it makes sense here. Okay. So before I do though, let me see if there's any questions so far. All right. So let me go to this whiteboard here and create another whiteboard. Okay. So what's going on is this thing is oscillating back and forth like this. Okay. All right, so there it goes like this and like that. Okay. And here's middle. Here's x equals 0. The velocity out here, let me do it in blue. Velocity out here is v equals 0. Okay, and the velocity over here was equal, that was the v max. I don't know what that was. Let me look at it again. What did we find v max? 0.7174. 0.7174. Okay, and let me do the amplitude here. Oh, you know what? I've been doing x in black, so let me do it in black here. X here, that's the amplitude. X is a at the end point, and that's equal to, what did we say that it was? 0.386. Sorry, 3.86. 3.86 centimeters. Okay. And there's 2 points in the cycle that we looked at. There was this point here, which was at x is equal to 2.5 centimeters. And the velocity there was 0.5 meters per second. Okay. Well, that's what I gave you. Like, if you read the problem, that was the original information I gave you. But I said, you know what? Let's also look at this other point here. All right. And you didn't know what the x value was, but we found that x value to be 1.564. 0.564, like that, centimeters. And there the velocity was 0.6 meters. Oh, that's terrible. Sorry, guys. 0.6 meters per second. Okay. Does this make sense? Let me make that decimal a little bit bigger right there. Does this make sense? Well, let's take a look here in the cycle. When you're, what color can I use? Green. Like when we're right here in the cycle, the velocity is 0. When we're here in the cycle, the velocity is like 0.7 and some change. Okay, so obviously as you move along the cycle here like that, your velocity increases from 0 to 0.7. Well, when you pass the 2.5 meter mark, you're at 0.5. When you're closer to equilibrium, you pass the 1.564 centimeter mark. Well, then you're going faster still. Okay, and so you could see that as you get closer to equilibrium, you're going to be going faster and faster and faster. In fact, I could have even picked another point. I mean, I don't think we need to belabor this, but suppose I said to you here, and let me say I gave you that. I said that that was x is equal to, I don't know, 1.0 centimeters, like that. Could you put boundary conditions on the velocity? And the answer is yes. It would have to be bigger than 0.6 meters per second, but less than 0.7174 meters per second. Okay, does everyone get why? Because it's speeding up. And so from here, from the 1 centimeter mark to the 0 centimeter mark, it has to be speeding up. And if it's speeding up, if it starts at 0.6 and it ends up at 0.7, then in the middle, it's got to be somewhere in between. Okay, and so this way you could see that when you look at your answers, you know that you're roughly in the right ballpark. It doesn't tell you that the answer is exactly right, but if you're outside of that range, you would definitely know that your answer is wrong. Okay, so that's it for today. There wasn't, I mean, I could multiply variations on this, but I think you're good for to work on the assignment. Okay, and this is one of the topics on the test, and the other topic will be Newton's laws. So I'll tell you more about the test. I haven't made it yet. I'll make it over the weekend. I'll tell you more about the test on Tuesday. So during our live chat on Tuesday, our live stream on Tuesday, I'll tell you a little bit more of what's on it, and we'll practice maybe another Newton force problem. Maybe a little bit more of the Newton's law problems because and planetary problems, just because that's a little bit further back, and then maybe we'll do some more of these as well. Okay, so that might be a little bit longer live stream, but there it is. All right. So if there's any questions, let me know in the chat. Otherwise, we're done for the day, and I don't know. It's kind of a rainy day. I was going to say enjoy it, but I don't know how much you can enjoy a rainy day having to stay inside all the time. So, all right, we're just waiting for any more questions. If anyone has any questions, otherwise, we'll call it a day or a class. All right, let me type in here. Any questions? Else we're done. Or any, I don't know. You too, Riandra. All right. Okay, guys, I think we're done. All right, let me end the live stream. Bye-bye.